Right, morning everyone. So I was going to give this kind of overview, as Rory said, on particle tracking modeling and why it's such a powerful and versatile technique for modeling things floating in the ocean. I see from the list of candidates there's people here who know as much about this topic as I do. So I'm afraid it may be slightly simplistic for some of you, but hopefully it will generate some discussion anyway for later on and introduce Swazik's talk in some kind of way. So obviously this is pretty much what the abstract said, that particle tracking models, PTMs, are pretty powerful tools for simulating transport and dispersion of material in the ocean. We do that by releasing numerical particles in a model and assigning appropriate properties and characteristics to the particle for whatever it is that we're trying to represent with them, whether that's dissolved substances, living organisms, particulate wastes, or more recently, quite a topical issue has been floating plastics and other buoyant materials. So those are the main kind of ideas I'm going to just talk quickly about. And obviously routine applications, particle tracking models have been used quite a lot in emergency response activities, particularly with oil spill modeling, which is kind of where, from my understanding, particle tracking model was first used actively in ocean marine research and search and rescue operations. But it's also obviously of interest to academics and for coastal zone management. So I'll try and cover some of these issues. I thought I'd just define what a PTM is, and of course I went to Wikipedia, so this must be correct. In computational fluid dynamics, Lagrangian particle tracking is a numerical technique for simulated tracking of Lagrangian particle paths within the Eulerian phase. So this shows, this is an old animation, but it kind of gets the point across. The black arrows represent currents, so that's the Eulerian phase. And then we release particles into that dynamic field, and they float around, moved by the currents and other physical processes. They're released as blue, so this kind of demonstrates some things I'll talk about in a bit more detail. But the particles, after a period of time, change state or phase or stage, depending on what you're talking about, and then they become purple. So it's we're tracking both the movement and the characteristics of the particles in that animation. So I'll talk more about details of this. So again, just what kind of properties or behaviors can we implement, and how does that change how the particles behave? Obviously, if we're looking at particulate material, sediments, particulate waste, then the particles may represent grains or flocks of grains. So you're looking at properties and behaviors such as particle settling and decay. For buoyant material, which again may be particulates like plastics, or it may be more like oil, which again is it's not a dissolved substance as such, but it's a fluid. So we're looking at processes like buoyancy, again decay, possibly evaporation for oil. So a slightly different set of properties and particle behaviors. For dissolved substances, with more passive, so there may be no behavior. We may just think that the material is passive in the water column and just moves completely with the water. It may still have decay, and it may have buoyancy, either positive or negative buoyancy, but it can just be a passive dissolved substance. And then perhaps most interesting, and I'll probably talk most about this, is biological organisms, such as larval dispersal. Particles may represent individual organisms, but obviously with larval dispersal, billions may be released from spawning sites or other sources. So your particles are more likely to represent clusters of organisms. So we call them superparticles. And the behaviors become more complex. We might have vertical movement, such as diurnal vertical migration. We've got mortality and growth, stage development that I've already mentioned, horizontal movement. But I think the point I wanted to get across with this talk, and really when I'm talking about the versatility, is that a lot of the behaviors that you can, between these different phases, can be attributed through just vertical movement, and it can be done very simply. So that's what I'm really going to focus on. Just a little bit of history. I just want to emphasize how far back these models go. I think they developed in the early 80s for oil spill response, largely, is my recollection, a bit of contaminant dispersion by Kath Allen, who was at the University of Lancaster. So the methods are very tried and tested, and the techniques are well established. It's a very reliable method. I think there are pitfalls involved in using particle tracking models, but these have been identified in those public. Kind of go through some of the things to watch out for and how to run particle tracking models to get robust and accurate results. The bit of maths that we need. So we have the movement of particles. So a particle is given an initial position x. So that's a position xy coordinates x, y, z in a three-dimensional space. And then we're going to move that particle around based on, I don't know if you can see my mouse, but I'm going to move it around anyway. Based on the velocity taken from my anime, they haven't worked very well. Okay, so based on physical processes which are in red, so that's the advection in 3D. So you're going to have horizontal and vertical currents. You're also going to have 3D diffusion. So again, that's simulated by what's known as a random walk model or a random displacement model. There are slightly different formulations of that. This is the one I've put up here. But the key term that I'm talking about is this additional movement due to biological activity or buoyancy or settling, which is this additional vertical movement that you can put in the advection term. So this WP, which can represent mostly, as I keep saying, vertical movement, but also horizontal. So of course, advection and diffusion are they happen, they're immutable, although part of the fun of models is you can switch them off. But largely that's a process that's going to happen. And we're looking at how can we modify the WP term to represent our particles or represent what we're trying to represent, and how does that affect the transport and dispersal. We also keep track of particle properties. That's the bottom line. I've just put a simple growth and decay expression in there. But again, it can include stage development, different biological stages. The mass can change due to evaporation or partitioning for chemicals. So there's all sorts of things you can track for each particle. So I'm going to go straight into some examples that I've found in recent literature. So Nicole Allison has been doing some nice work on plastics around the west coast of Scotland. Plastics are relatively simple and they're buoyant, so they sit on the water sea surface. So you can do that either by setting a buoyancy term, so the WP is greater than 0, which lifts everything up to the surface, or even simply you just set your depths of your particles to 0 and then you ignore the vertical velocity and the vertical diffusion in the solution movement, solving those terms. So that the depth of your particles is always 0. Nicole also included a wind drift term with things floating on the material on the surface. They might have an extra wind drag, so she included a wind drift term of different percentages of the wind speed. So that's that alpha parameter. And then she looked at, I think in this paper they were interested in sources of plastics from the Clyde Sea. So they released lots of material in the Clyde and wanted to see how much of it drifted up the west coast of Scotland. So they had observations over a long period from the Conservation Society, Marine Conservation Society surveys. That's the observations on the left-hand side of the left-hand plot, which shows particles going all over the coast. and they had some idea that a large proportion of this came from the Clyde. And then in the model, which is on the right, they run the model for a year, releasing particles from the right and watching how they drifted out of the Clyde Sea and up the west coast of Scotland for different wind drifts and different beaching. So they modeled different, although the transport and advection was quite simple, they had a more complex beaching response in their model, so that the particles either stuck to the beach or randomly were refloated and drifted off again, or were assigned a beach type. So there's cliffs or sticky beach. And again, those different responses can be shown in the right-hand side. Again, I'm only talking, I don't really want to talk in these examples about the details of the results because I wasn't involved. I'm really interested in here about how they just model the different types of material. So this is a paper by Stephen Gary and Alan Fox and their colleagues. So we're looking at larval dispersal connectivity over the North Atlantic. So here they've got a much more complex range of behaviors, but again, looking mainly at swimming speeds and how that, so again, it's vertical movement of the particles and how that affects the dispersion. But the response is more complex because it depends on maturity of the particles, of the larvae. And then that affects how fast the particles were swimming. So, and you can experiment with all of these. They had different upward swim speeds, different downward swim speeds. The age of competency varied when the particles looked for somewhere to settle. So they moved from a pelagic phase to a settling phase, and so of course the behavior changes when they change their stage. And they showed nice distributions across the North Atlantic of released positions, which are the darker colors, where all those particles spread based on the different kinds of behaviors. And in the bottom left-hand corner there is just the spreading area for different areas based on some of those different experiments. So you can see changing the parameter set obviously affects the dispersion quite a lot. I'm going to come back to larval dispersal a bit later, talk a bit more about that. In aquaculture, we use particle tracking models a lot for particulate waste. Fish farms produce waste feed and fish feces that has settling properties. The feed and feces settle out through the seabed as well as being advected side to side by the currents. So the particles are given, we have two types of particles, one type representing feed with a settling velocity appropriate for feed, and then another type of particle for fish feces with a different settling velocity. So typically we run the model for a year with inputs based on how much feed and how much waste is produced, and the particles settle out and produce a footprint on the seabed underneath the pens. We're currently using a model called New Depomod, developed at SAMS, published by Tom Adams 4 years ago now. These plots are really old, from Chris Cromie's paper in 2002, who developed the original Depomod model. And although the simple model is just the settling, New Depomod includes now more complex seabed interactions, so the particles can resuspend, be eroded from the seabed and then moved again. So again, you get more complex behavior, all based largely on this vertical velocity or vertical speed. Let's just, can I close that? Right. Simplest case is probably dissolved substances, so pollutants, although, like I said, they can be passive, where you just set the WP to 0, or they can be buoyant, or absorb to particulates, in which case you might give them a small settling velocity, or they may be negatively buoyant. So again, you can have a slightly settling particles representing droplets of dissolved material. The particle properties for this, for chemicals, may be more complex. So you may have degradation and volatilization, partitioning between phases. So all that can be modeled. There's a recent paper out by Agito, who's developing this chemical drift model, which does all this chemical properties within the ocean drift framework, which is the Lagrangian advection diffusion framework. And you can see how these plots just show different dispersion patterns of particles based on the different phases, whether they're dissolved, which are the blue dots, attached to particles, which are the green dots, as suspended particulate matter, or whether they're in the sediment phase, which means they've attached to particles and settled out. And obviously, you get very different dispersion patterns with the same model, just by different vertical behaviors. I'm going to talk a bit about sea lice modeling, because we do that a lot and have been doing that a lot for the last few years in Scotland. It's a really interesting problem. Sea lice are a natural ectoparasite. One of them, the salmon louse, specifically targets salmon and sea trout, both farmed and wild. So the adult females, which are attached to a fish, release eggs into the water. Those eggs disperse and hatch into a nauplius stage, which isn't infective. So they're still floating around. After some time, which is temperature dependent, the nauplii stage molts into an infectious copepodid stage. And that stage then has to find a new host fish before its energy resources become depleted. They don't feed. They're based on energy reserves from the eggs, and they must find a new host before they deplete those energy resources. So this is an interesting problem, because there's two stages, the nauplius and the copepodid. They have different behaviors. We're increasingly finding out how different those behaviors are. And it's interesting because the physics of inshore waters in Scotland and elsewhere, in Norway, where there's a lot of fish farms as well, obviously. The physics are very complicated. We have, this is the side view of a fjord, or like a Scottish sea loch. So we have a surface layer where fresh water's coming in, and that tends to flow seawards out of the sea loch. It's compensated by an intermediate layer that's flowing towards the landward end of the loch. And then you often have sills with basin water trapped beneath, which is mostly quite quiescent. Occasionally it gets disturbed by dense bottom currents. Those events are usually not rare, but not common. Intermittent. So we have the stratified waters, and then of course with completely different current patterns. So then the vertical positioning of larvae in that becomes very important, affecting the dispersal properties. So Swazek Ghani, who's speaking next, has produced a nice paper on looking at how this vertical swimming behavior affects the dispersion of lice in the Firth of Lorn and Loch Linney and the Firth of Lorn. So we know that the swimming, sinking speeds of lice larvae may depend on the stage. So whether they're nauplii or copepod, they have different swimming speeds and different responses. So they may have, it's not fully understood yet. So they may have, they may run a reverse down or vertical migration. So they're partly phototactics. So they come to the surface during daylight hours and sink down at nights. We think they avoid low salinity water. So they might swim down if they encounter low salinity water. And the nauplius stage, there's some theories that the nauplius stage seek out warmer water so that they can develop into the infectious stage quicker. So that's a different response. So in the models, first of all, we have to track the temperature dependent stage. So we think that the nauplius stage lasts about 40-degree days. So if the water's 10 degrees, then they would change stage after 4 days. If it's 8 degrees, they change stage after 5 days. But of course, temperature isn't constant. Each larvae, and each particle has its own life experience. So in the model, we integrate the time experience, the temperature experienced by each particle over time until we get to that 40-degree days, and then they change stage. So we keep track of the stage. We account for mortality. There's a 1% loss per hour is what's generally used. And then we have this hierarchy of behavioral responses to determine how they're swimming. So we need to know the larval stage. Then we look at the time of day or the light intensity. So are they swimming up or are they swimming down, and depending on light or time of day. And then we look at the salinity, and is that low salinity threshold met? Are they going to swim down to avoid low salinity water? So we step through this process to end up with the appropriate swimming speed and behavior at that moment in time for that particular particle. So Swazix published this earlier this year, showing all these different responses in the vertical over time. So this is the concentration of particles or lice for different behaviors. So you can see there's very different patterns, and as we see in inshore waters with the stratified flows, that it has a big impact on how these lice disperse. And then you can look at numbers of in a particular area, how many particles remain. So as it's shown here, different retention numbers within a box in Loughlin. So quite nice parameters and parameter exploration, but all again based on this simple W term within a particle tracking model. There's a couple of other applications just to mention briefly. Backwards tracking, particle tracking models can be run backwards. That's useful for identifying potential sources of observations. For example, beached plastics. You can start where you know the material was found and work backwards in time. So there's a paper there showing how that might work. And increasingly, people are looking at salmon and fish migration. That's quite complicated because it involves applying a horizontal swimming speed. So we're not just looking at the swimming in the vertical, we're now looking at swimming in the horizontal. And to do that, we need swimming rules. And that's a bit harder to come by. James Ownsley published some work on this a few years ago, and Aislinn Borland has been doing some nice stuff on this at Strathclyde for her PhD. I was just going to have a quick mention on analysis. We can get a lot of metrics out of particle tracking models. Obviously, the particle locations and movement, I showed an animation at the start, which is just moving the particles around and looking at that. That can be quite misleading because particles, when you plot them, if we're often representing microscopic organisms, and yet the size of the particles, in order to see them, it'd be like small oil tankers floating around. So these particle plots can be quite deceptive. So better to calculate concentrations. Time series could be very useful for diagnostics. We want to test whether the model is fit for purpose, looking at numbers of particles, time steps. So you need to, if you change your particle numbers or time step, then obviously your time series shouldn't change too much. If you have a big change, it means you're probably not using enough particles. We can look at, so time series are useful for diagnostics. We can look at ultimate distributions and particle fates, transport pathways, obviously, and concentrations. To calculate concentrations, you need a grid, and you count your particles up on a grid, whether that's a square grid or an unstructured grid. Increasingly, we're using unstructured mesh hydrodynamic models. I always have a preference for calculating concentrations on square grids because it gives you a resolution of your calculated concentration. Whereas if you're on a variable mesh grid, that resolution varies because your area that you're counting particles in is different for each triangle, and therefore you don't have a minimum resolution or a clear idea of what the resolution of your concentrations are. And of course we can get derived outputs from those basic outputs, such as retention and flushing times, which I showed from Swazix, and connectivity between sites, which is important for the larval dispersal. So I think that's a very fast overview. I have no idea whether I've gone to time or not. It's a very fast overview of why I think particle tracking models are so powerful. Just by simple changes in the coding or in the parameter set, you can parameterize and model dispersal of very different materials in the ocean. And just to bear in mind that there are pitfalls that should be avoided, so to ensure sensible and robust results. So read the essential literature. So thanks for listening.